Okay, yeah. Hi, everyone. Thank you for tuning in. So this week, we're very lucky to have Nicolas Papernot. He's an assistant professor at has had many influential works in the areas of security and privacy and machine learning, including outstanding paper at iClear 2022, best paper iClear 2017, among many other numerous awards and honors, including the Alfred Sloan Fellowship. So, yeah, Nick, really looking forward to your presentation today on
Yeah, thank you, Tyler,
machine
for the introduction. I'm
today.
very happy to be here virtually today. And as you mentioned, I'll be giving a talk going through both sort of implementations and definitions for machine unlearning. And this is work that I've done since 2019 with a few members in my group here at the University of Toronto. And in particular, a lot of the work that I'll talk about was done by my PhD student Envith Tudi, um, who made a lot of the slides that I adapted for this presentation. And so the story behind his very convenient envith.com URL is that his dad bought it when he was born. So he's lucky to have that domain now that he's an academic. It's very convenient. So what I'll start with today is really motivations for why we would want to delete training data. And when we started doing this work, there was really a lot of interest in the deletion of training data from the perspective of privacy. So this is the third bullet in this list here, where there was a lot of talk around the GDPR in the European Union. And since then, a lot of countries have developed or drafted several similar legislation, like, for instance, in the United States, California has the Consumer Privacy Act, and in Canada, we have Bill C-27, which are putting forward sort of this notion of giving individuals control of their data, meaning that they should be able to retract access that they've granted to their data. And so in the context of machine learning, we have to now ask ourselves, how do we remove data that the model has trained from once it has been deployed? And other motivations that we considered for this work include more sort of security-centric motivations. So for instance, there's a lot of concerns, especially as machine learning models are trained from data sets that have increasingly low provenance guarantees, that some of the data that they're being trained on could be poisoned by malicious adversaries. And so there again, that gives you motivation for once you've deployed a model to have a technique that you can use to then remove the effect of these maliciously manipulated training points. And then a few years ago, we thought also about sort of, well, it could also be useful to have unlearning in the context of sort of copyright claims, especially when machine learning models are used to make outputs, which are data themselves. And so this has, of course, gained a lot of attention recently as sort of progress in generative machine learning has really picked up in terms of pace. So these are questions that are really being raised now in sort of the courts. And so this is really relevant. But for the rest of the talk, I'm going to focus on the third motivation, simply because it's been sort of the main motivation for most papers that you'll read on learning in the field. And I will try to comment throughout the talk when it's relevant, what differences we could imagine if we were to look at unlearning for these two other motivations. So if we think in practice, what can we do if we'd like to unlearn? Well, very intuitively, we could imagine that the naive solution would be to retrain the model from scratch. And this is not such a naive solution in the sense that it comes with very strong and intuitive guarantees for the end users. So they will understand that once you've done this retraining, their data no longer influences the model. And so the question now is, well, can we do better than this baseline? And better here in particular means, can we spend less compute than is required to retrain the model from scratch? So in this first paper here at the bottom of the screen, what we've done is we've looked at, well, what if we proactively changed the way that we train the model to then make it easier to unlearn? And here for the rest of the talk, I'll assume that I'm trying to train some form of deep neural network, in particular with stochastic gradient descent. This is because that's the setting in which the cost of retraining from scratch is sort of significant, and for which there is no sort of closed form solution to unlearning. And so here in this particular work, what we've done is we thought about, well, can we modify the stochastic gradient descent procedure such that we end up with models that are easier to unlearn? And in particular, what we did is we introduced two knobs, two changes. The first one is that we sharded the training data. So here you have your original training set. We sharded it in multiple partitions. So here we've depicted S partitions. And each of these shards is going to be used to train an independent model. So rather than have one large model trained on the entire data set, we're actually training an ensemble of models. And this has an intuitive benefit, which is that now if I want to unlearn this red piece of data, I only need to retrain the model in the ensemble that analyzed that data during training. So this is going to be sort of easier to do in terms of compute required. It does come at the cost of accuracy, in the sense that if I train too many of these models in the ensemble, each of them becomes a weak learner and doesn't have enough data to learn from. So what we did in addition to that is we then looked at each of these shards and further partitioned these shards into slices. And here the idea is that rather than train the model in sort of the usual way with epochs that analyze for each epoch the entire training set, what we've done here is we've sliced the data and then we start training only on one of the slices of the data. What that means is, for instance, we'll start by training from the random initialization on, let's say, 10% of the data in the shard. And before we introduce another 10% of the data, we're going to save the model parameters. And then only at that point, we'll introduce additional data. And so if we do this in sort of in such a way that we save the parameter states before every slice that we introduce from the shard, then essentially once we want to unlearn one of these points here, we can revert the training procedure back to the last state that was known before that piece of data was introduced. And so that gives us essentially a knob where we can trade the storage cost, because the more slices we introduce, the more parameter vectors we have to save, for sort of a lower compute cost once we actually want to unlearn. And so if we look at sort of, if we put these things together, what we're able to do with this approach, which we call CISA, for sharded isolated sliced aggregated training, is essentially we outperform a baseline where we retrain a single large model on the entire data set without the point to be unlearned, by having much smaller sort of retraining time compared to that baseline. So that's what you can see here. All the three curves here are different instances of CISA with increasingly more shards. And you can see they all outperform in terms of the analytical time that's required to process these unlearning requests. But of course, as you increase the number of shards, you can see the accuracy starts to decrease, as I mentioned below. And the other baseline we have here are these three curves, where we are instead just training on a fraction of data, because of course, if we never trained on a piece of data, we don't have to unlearn it. And so here you can see that the retraining time is much smaller, but we pay a very steep price in accuracy. And so you can think of CISA as sort of interpolating between some of these baselines and giving you sort of practical ways to tune how much storage, how much accuracy you want to pay in order to be able to retrain. And I think this kind of setup is not completely artificial. In particular, it comes in sort of as a natural fit for pipelines where the data is sort of coming in a streaming fashion. Because what you can imagine there is that as more data comes in, you can sort of buffer that data until you have enough data to train a new model for your ensemble. And then at that time, you essentially delete the oldest piece of data, the oldest model in the ensemble. And so you kind of have this rolling window of models that you can not only easily unlearn, but that also adapt to the distribution drift. So that's essentially what we can do in terms of training deep neural networks from scratch. And despite the improvements that CISA has brought, there's really still a very steep cost in retraining, because we're still retraining at least part of the ensemble as the unlearning requests are coming in. And so what we've seen recently is that there is this sort of shift towards this paradigm where we train a model from scratch from a random initialization to a paradigm where you will sort of adapt an existing model to the task that you have in mind. And so this offers us sort of a different paradigm that we can actually exploit to improve our ability to unlearn. In particular, I'll present sort of two key paradigms that people have been discussing a lot. First one is pretty easy, is fine tuning. So you take your pre-trained model and you add a bit of downstream task data and you continue training on that data. And so for that paradigm, you can see how you could use something like CISA to make that easier to unlearn. But what's interesting is this novel paradigm where there's no sort of additional training that's done. Instead, we select a few samples from the downstream task data set, and we include those at inference in addition to the input that we'd like to predict on. And so this is known as prompting. And so there's an interesting question, which is, can we do better in terms of unlearning than what we were able to achieve with sort of unlearning the fine-tuning here as done previously? And so here we have to look a little bit more carefully how we actually select the examples that go into the prompts. And so sort of the most basic approach you can think of is, well, we're just going to randomly select some of the examples and include those in the prompts. And that's going to be very easy to unlearn because I can just replace the sample with another sample. The downside with that is that typically that doesn't achieve very good prediction accuracy. So people have come up with a lot of heuristics to improve the accuracy by selecting the examples that go in the prompts in sort of a more sophisticated way. And in particular, a strategy that comes up sort of often is to pick the points that are the closest to centroids as you perform a k-means analysis. And so this is nice in the sense that what people have shown is that the coverage that this provides you from in terms of the downstream data set increases the accuracy compared to randomly selecting samples. But in terms of unlearning, this has a downside, which is that now if we want to unlearn, we have to repeat the k-means analysis. And so what we showed in this preprint here at the bottom of the screen is that if we want to sort of decrease the cost of unlearning for prompts, what we can do is we can build on prior work that introduced a quantized k-means analysis, where we're going to use this quantized k-means analysis to pick the points that are going to be included in the prompt. And the nice thing about this is that now, because we are quantizing k-means analysis, the centroid assignments are going to be more stable as we remove individual points from the downstream data set. And so what this means is that we're not going to have to repeat the k-means analysis all the time. And so what we see here is that with this quantization, we are able to essentially trade off the cost of unlearning with prediction accuracy, because of course, the more you quantize, the lower the accuracy will be eventually. And so if we put all of these pieces together, what we've done here is compare an approach which is based on prompting and an approach that is based on fine-tuning. And in particular here, we've instantiated with CISA and try to get a sense of what's the improvement in terms of unlearning when we compare these two approaches. Here, we've just included for reference a baseline which doesn't do any form of task adaptation. And the tasks that we're looking at here, there are more tasks in the paper, but this one makes it easier to explain the trade-offs. This is intent recognition, which is essentially talking to a voice assistant on your phone and trying to perform a particular action, and you're trying to figure out what the action in question is. And so on the vertical axis, we have some normalized performance in terms of the accuracy, where lower numbers are worse and higher numbers are better. And here we have sort of three instantiations of our prompting-based approach, here with increasingly more centroids, meaning increasingly more examples in the prompts. And so the more examples you include, the higher the accuracy is. And on the right, you have multiple instantiations of CISA with varying shard numbers. So here it's the opposite. As you increase the number of shards, the performance decreases, as I've discussed before. What you can see here is now, in terms of unlearning costs, the nice thing about increasing the number of shards is that I decrease the unlearning cost, the operation of unlearning. Instead, for erase, the cost is more or less constant if we sort of ignore the minor effect in the change in the data set size. But what's important to notice here is that in both cases, we're actually increasing the inference cost as we make it sort of easier to unlearn. And in particular with CISA, we have to repeat the inference for each of the models in the ensemble. And in terms of erase, what we have to take into account now is that at inference, I'm adding multiple examples in the prompts, so that increases the cost of inference as well. And so what this figure tells us is that in some settings, we're able to outperform the unlearning approach that are based on fine-tuning with prompting-based approaches. But the catch is that this outperformance depends on the number of inference requests that we're going to have to process after each unlearning request. And so that's an important point, I think, because in most prior work, what people had considered is really decreasing the cost of unlearning itself. And that is the operation where you modify the model. But here, what we show is that it's also important to capture the increased prediction costs. When we're actually going to deploy the unlearned model, the inference costs can also increase because of what we've done through the unlearning operation, or to make that unlearning operation cheaper. And so we really have to look at this holistic cost assessment that captures not only how expensive it is to unlearn, but also how expensive it is to deploy the unlearned model once we've done that. And so here, this is very important, and that's when you can start making conclusions as to whether fine-tuning or prompting is better, for instance, for this particular task. So this is a good point to stop if anyone has questions before I start diving into definitions.
I have a broad one, Nicolas.
Yeah.
About the metric for the quality of unlearning, can you comment on that? It's not a straightforward thing to measure, right? Like
Yeah.
Who has unlearned the data, and can you comment on different ways that you can measure unlearning?
Yeah, so I'm actually going to talk about this right now in this slide. But what I'll say is that for now, what I've assumed is that we want to achieve exact unlearning, which means that the distribution of models that we achieve here by training from the initial data set and then unlearning should be the same as the distribution of models we would have achieved without seeing the point to be unlearned in the first place and directly training in that setting. And so that's what we've achieved with CISA, with sort of the prompting-based approach I just talked about. But now, sort of what I want to talk about is, well, these approaches have their own limitations in the sense that in terms of CISA, the cost is still fairly high. And in terms of arrays, the approach for prompting-based models, it's of course specific to downstream task adaptation. And so what I'll talk about in the rest of the talk is essentially how we can move away from this exact unlearning definition, which is pretty strict, to essentially hope to scale to other pipelines, in particular, the machine learning pipelines that are used, for instance, to pre-train these models that are being task adapted. Does that answer your question?
Absolutely, thank you. Just one clarification question.
Yep.
When you say distribution of models, are you talking about the output distribution, or are you talking about, in a Bayesian sense, about the actual distribution in a functional space?
So that is another question that I will cover in the next slides. There are multiple ways to define this. So these are very good questions. So essentially, what I will talk about now is sort of, first of all, what does this sort of magic process of unlearning look like when we're not talking about exact unlearning, and also what it means for these distributions to be equal. And I should add sort of a spoiler alert, which is that I do not have the answer to this question here at the top. This is sort of still an open problem. But what I'll try to do is essentially highlight two key considerations that we've identified through the different projects that we've worked on, and sort of how we are at in terms of defining the right open problem to think about. So in terms of the techniques itself, for unlearning, when we're not trying to do exact unlearning, there are lots and lots of approaches that have been proposed in the field. And so you can pick your favorite ideas from this list. I'll mention a few: gradient descent on the data to be unlearned, continued training without the data to be unlearned, pruning, reinitializing some of the weights using a different loss. So these are all techniques people have tried in terms of sort of non-exact, so inexact unlearning. And you'll notice that some of them can be combined. But really the main limitation of all this work is that we're now no longer getting this exact unlearning guarantee. And so we have to define sort of a success metric for what it means to have unlearned. And so as we were just talking, here, what this means is we have to compare these models that these unlearning techniques output with the models that we would have obtained by retraining from scratch, essentially. And so this comparison can be done in lots and lots of different ways. And in particular, there are two classes of approaches. So some will compare the models in the weight space. The issue there is essentially that you can have models that have identical predictions and very, very different weights, right? You can see that, for instance, by shuffling some of the neurons in a layer on the neural network. And so that means that these kinds of metrics are very hard to interpret, right? It's not necessary that having sort of small weight distances is very meaningful. The other way you could do this is, well, you could look at output space differences, or function space if you want. And essentially the main limitation is when you can define this sort of on paper, but then once you actually need to, in practice, measure these types of distances, you typically need to sample some points from the data distribution. And so there, of course, the difference estimation is going to depend a lot on the points that you sample. And so that's also not ideal. And so for this reason, this is sort of the first challenge, is sort of how do we even compare the models that we output? And so I'll talk a little bit about sort of how people have approached this. And in particular, one line of work that has gained a lot of attention is, well, maybe we don't need to reinvent the wheel, and we can look at other privacy definitions that have emerged. And in particular, we can look at differential privacy. And so in differential privacy, the nice thing is that we have now an algorithmic centric definition of privacy rather than a definition that is sort of focused on the models themselves. And so what that means is that we have good hope of circumventing some of these limitations here that I pointed at the bottom of the slide. And in particular, what differential privacy is asking for is, if we have our training algorithm, essentially an adversary that's observing the outputs of the algorithm shouldn't be able to tell whether the algorithm was processing this first data set here, which contains a bunch of records, including this green record here, or the second pool, except that it doesn't contain that particular record, or that record was a different record. And so what we're seeing here is that the more indistinguishable these two settings are, essentially, the less there is a need to unlearn, in the sense that this particular point here doesn't really influence the parameters or the predictions, if you want, of the model that I'm outputting. And here, this is true for if we prove that an algorithm is differentially private. We prove so for every possible pair of data sets here that are only different in one of their training points. So essentially, it doesn't matter who wants to unlearn. We'll be able to essentially tell them, well, no, your point didn't have a significant impact on the model, so we don't really need to unlearn. And in particular, differential privacy quantifies this level of indistinguishability through a parameter that's written down as epsilon. And when that parameter is close to 0, essentially, we have very strong indistinguishability, so we shouldn't need to unlearn. So that's sort of hopeful, but there's still a number of limitations here. The first one is that the differential privacy guarantee, as I just mentioned, bounds how much we learn from every possible training example, right? And so this is a bit too strict of a guarantee, because in unlearning, we typically want to unlearn a small subset of examples. And so we don't really need to have this guarantee that holds for all the other points that we don't need to unlearn. The second limitation is related to the first one, which is that just like it is difficult in sort of normal privacy preserving machine learning, here we're going to have this question of how do we set what is an acceptable privacy budget epsilon, meaning how indistinguishable these two settings need to be. And that's very difficult in practice, because what we'd like ideally is for epsilon to be 0. But if we do that, we'll have no accuracy for the models we train. And so there's no point in sort of deploying this. So in approximate unlearning, we're essentially going to have the same challenges as to how low of a value of epsilon we need to have. And in particular, this is going to be made more difficult by the fact that we might want to unlearn multiple points. And so if we frame this in terms of differential privacy, we now have a group guarantee where we need to degrade the value of epsilon proportionally to the number of people that want to unlearn. And so what that means is that that's going to make it even harder to pick that value of epsilon. And so in general, the takeaway here is, sure, we could use differential privacy for approximate unlearning, but most likely we'll end up paying too much for the privacy guarantee. And so we have to think about how do we relax the definition. And I'll come back to that point a little bit later in the talk. In particular, how do we relax the definition? Well, we could think about trying to instantiate sort of a more practical way of measuring how different these two settings are. And this is something that people have done in a field known as privacy auditing, where the idea is to try and understand, given a particular model here, if I'm an auditor or an end user, can I understand how much leakage is happening in practice? And in this case, what I want to know is, did the model train or did it not train on this particular point? And if I can answer this question, then I have a metric for unlearning, in the sense that I just need to make sure that after I've unlearned, the outcome of this audit is that the point was not used to train. So here, this is very interesting, again, to consider, especially given how much progress there has been coming up with these verifier approaches to audit privacy-preserving machine learning. But the main problem is that these attacks remain suboptimal. And so I'll explain two ways that they're suboptimal and sort of highlight the consequences to unlearning. So the first problem here is that if we take a model, look at sort of run a membership. So by the way, this type of attack of audit is known as a membership inference attack. And so if we run a membership inference attack on the model and we rank the points by how strong their membership inference signal is, now if we remove the points for which membership inference is the most successful and retrain the model, what we would expect is perhaps that, well, the remaining points will have low membership inference signal, but that's actually not what happens. What happens is that new points emerge with high membership inference signal. And so that's why we call this sort of privacy onion effect, in the sense that once you remove the outer layer of points that are the most sensitive in terms of privacy, and for which we can tell they were used in the training set, you expose a new layer of points that are now easy to identify as members of the training set. And so what that means is that essentially the ability to tell whether or not you're part of the training set depends on the other points in the training set. And so if you rephrase that, giving the ability of to individuals to have control on their data essentially potentially exposes the privacy of other individuals. Because now if I remove my data from the training set, I might all of a sudden expose your privacy, your private information in your data, even though previously you thought that your privacy was not exposed because the membership inference attack failed. So that's the first reason why it's really hard to rely on membership inference as a way to evaluate unlearning techniques, because essentially you would need to repeatedly run this audit, and you would never have a reliable way to assess the results because they always depend on the other points in the training set. The other limitation that we've identified here, and I've shown this in this graph here, is that if you look at the red bars, these are sort of the epochs at which we've analyzed a particular training point. And here, so this is just the epoch number, so as training progresses. And the different curves are different metrics to assess how strong the membership inference signal is. What you can see is that naturally, as I stop analyzing the point during training, membership inference signal starts to degrade. And so again, that makes it very difficult to know how strong of a membership inference signal I need before I conclude that the point was used to train the model, because the outcome of the test will be different here and here, for instance, in the training run. And so this led us to write this last preprint here at the bottom, where we really showed that if we want to use membership inference to evaluate unlearning techniques, we have to be very careful in the conclusions we draw, because these conclusions are sort of conditional on how good of an attack we have at the present time. And so it's very hard to sort of draw conclusive evaluations of whether or not a particular unlearning technique is successful. And so in order to sort of address these limitations, we've tried to think about, could we provide additional information to the auditor in order to make it easier for them to tell whether or not we've actually trained on a particular point. So here, if you remember, I had this little game here. And so you could think about, well, what if I give not only the model to the verifier, but also some sort of proof? So some additional information about how I obtain this model to hopefully make the verifier's job easier to reliably tell whether or not I trained on a particular point. And so one approach that we considered is this, what we call this proof of learning here, which is very simple. It basically records all the intermediate model state that I've achieved during my gradient descent, along with all the indices of the training data points that I've used to compute each of these gradient descent steps. So for instance, this could be an individual training example, or it could be a mini batch if you're using mini batch stochastic gradient descent, and each arrow here is a gradient descent step. And so of course here, if you have such a proof, you give it to the verifier. Sort of the naive strategy you can think of is, well, the verifier just goes through the indices of the training points that were used for each of these steps. And to unlearn, you basically have to produce a different proof which no longer contains the point to be unlearned in each of these individual steps. And so that's appealing. But here again, there is sort of a fundamental limitation to this kind of approaches. And the problem is that essentially we can take each of these individual steps and replace the mini batch that was used to compute that gradient in particular with a different mini batch that will lead to the same gradient. Okay, and we can actually construct these mini batches greedily. So in this paper here, manipulating SGD with data ordering attacks, what we showed is essentially, given a particular gradient descent step that you want to achieve, you can sample greedily from another data set and assemble a mini batch that will give you exactly that gradient descent step. And so essentially what we've shown here is that we cannot rely on these proofs to reliably assess whether or not a particular point was used in the training set, because a malicious model trainer could always obtain the proof first from a particular data set and then manufacture a second proof that no longer contains some of the points from that data set. And so what this really shows is that the kinds of guarantees we need are algorithmic. We cannot rely on analyzing sort of what we have in the model space. For instance, here in the weight space, we have to think about how did we obtain this model in particular, and in particular, how likely it is that we would have found the trajectory that we found if we didn't have access to the point that we want to unlearn. And so this is, again, where we have these very nice connections to differential privacy. And what we've done in my group recently is to try and assess essentially whether we can bound the success of membership inference specifically, rather than bound the success of any privacy attack, which is what differential privacy is trying to do. So what we're doing now is we're taking this individual game here, where the verifier is trying to tell whether the point was a member or not, and trying to bound the success of that specific attack. And what we showed is that this allows us to identify additional factors that allow us to provide tighter guarantees at sort of a smaller expense in terms of model accuracy. The second approach that we've tried to follow is to think about differential privacy guarantees that are data dependent rather than data independent. So the way that people typically reason about differential privacy is by essentially proving that the algorithm is differentially private for any possible pair of data sets that differ by one training example. And so this is very worst case analysis, whereas here for data dependent guarantees, we're trying to obtain this guarantee, but for a fixed data set of interest. And so this allows us to tell for each of the individual points in that data set, how much is that point really being exposed as we train on it with our machine learning algorithm. So these are two directions that we're currently exploring. And then the third attempt that we've been looking at, which is sort of a last resort solution, is to use cryptography. And so here, if you use verified computing, you have this inherent ability to sort of run this model here and its training algorithm within sort of this verified computing environment. And so what this means is that you can now cryptographically prove which of the points were used and were not used in the training set. The main disadvantage of this type of approach is that it does not scale. So we've been able to implement this verified computing approach, but for a neural network that has, I believe, 3 to 5 neurons. So not the kind of neural network for which you would want to have unlearning guarantees. So to conclude, I will say there are really 3 points that I want to stress. The first one is that we want to capture both the cost of the exact unlearning operation itself, but also the increases in the inference costs. And this is the point that I made initially in the erase paper at the very beginning of the presentation, is that a lot of attention has been placed on decreasing the cost of the unlearning operation itself, but we have to also capture the cost of deploying that unlearned model. The second takeaway is what I've just talked about in sort of relaxing the definitions of approximate unlearning. First takeaway is we need to do this algorithmically, and this is why differential privacy is appealing, but we have to do so in a way that will consider the interactions between these different training points. And so this is, I think, not a purely computer science problem in the sense that we essentially have this tension between giving controls to individuals and sort of having this privacy notion at the level of society. And then lastly, we want to be able to take into account these different motivations as we relax the definition of unlearning. And in particular, I've talked throughout this entire talk about sort of the privacy-related definitions of unlearning, but we can imagine that in the poisoning or the copyright scenarios, there might be other ways that we can relax what it means to unlearn to sort of mitigate the cost in terms of accuracy. And in particular, if we have poisoning as a motivation, what's interesting is that the entity that's interested in the unlearning guarantee is now the model trainer itself, not sort of a different user. And so that, I think, gives us an opportunity to relax things differently. And the last thing that we're working on currently with my group is really to understand better how data sets lead optimizers to prioritize, to consider specific gradient descent trajectories, because we think that's going to be very important when it comes to providing verifiable guarantees for unlearning. And so these are some of the directions here, for instance, that I've mentioned in terms of bounding membership inference stacks or providing data-dependent guarantees. With this concludes my talk. I just want to advertise that we're organizing secure and trustworthy machine learning, the second iteration of this conference on UFT campus between the 9th and 11th of April. So if you'd like to attend, I'd love to see you there. And with that, I'll thank again our sponsors and my group members for all their work on the projects that I've talked about today. And I'm happy to take any questions you have.
Thank you. So we do have the Q&A open. I guess while waiting for a couple questions to come in, one I had on that conclusion slide, you mentioned this societal aspects, and wondering if you can maybe discuss a little bit more of some of your, I guess, potential concerns there.
Yeah. So essentially, what happens in terms of the societal aspects is that if you think about the point that I mentioned with the privacy onion is if you give individuals the ability to protect their own privacy, so for instance, if you give people the ability to unlearn their own data, this can have negative consequences for other people that are included in the data set. And so, for instance, in the privacy onion paper, what we showed is that if we remove, imagine that the people with the highest membership inference signal make a request to unlearn their data, then what you'll end up with is that the people whose data was initially not vulnerable to a membership inference attack will now be exposed potentially to the membership inference attack. And so, whereas their privacy was initially sort of protected, quote unquote, because the current attacks couldn't expose their data, now because someone else requested to delete their data, all of a sudden, their privacy is sort of worse off than they were initially. And so, I think that makes it difficult to reason about what we want to achieve without sort of capturing this societal aspect in the sense that we do want to trade off sort of individual privacy with societal level privacy. And this is even worse, these kinds of trade-offs are worse in data sets where fairness comes into play, because you now have a distribution, for instance, that is heavy-tailed. And so you might have very few points from, for instance, from an underrepresented group in the data set. And so if one of these points decides to unlearn, they will have a very significant impact on the predictions that the model makes for other points that are members of that minority. And so in this particular case, you can see how, again, there is sort of some societal questions that need to be answered as to how you handle these trade-offs, basically.
Yeah, I guess I'm thinking personally coming from more of like a social network perspective of social media, recommender systems, search engines, that potentially adversaries constructing their data in such a way, knowing that they're going to request the unlearning of their data, and how that might potentially impact this even more than just benign users requesting their removal, and how that's going to impact others in the data set, but adversaries maybe specifically constructing their data in such a way that they're planning to request this.
Oh yeah, absolutely. So there is actually some work that looks at this in the context of unlearning. I'd be happy to send it to you in an email afterwards.
Okay.
But you're absolutely right. You can essentially, one downside of unlearning is you're releasing sort of differential checkpoints about your model. So now you're sort of exposing, if people are able to sort of observe your model as it's unlearning, so before and after it unlearns, they get additional information about sort of potentially the data set. And so this can also have negative consequences, even for the person that decides to unlearn, because now if you have access to the model before and after it unlearns, you see exactly what was needed to be modified in order to remove that particular point's contribution.
Really exciting. Thanks.
So I have another question regarding the trajectory of training. I'm thinking that the batch size is going to actually play a very important role there in deciding whether a point was trained, what was used in training of the network or not. Do you have any particular comments on the effect of batch size on making the problem easier or more difficult?
Yeah, so typically what happens is that the if you look at, for instance, the results that I talked about on forging, essentially, if you have a larger mini batch size, then it's sort of intuitively, it's easier to find, yeah, I think it's easier to find points that will sort of replace the contribution of the point to be unlearned. So the smaller the mini batch size, the more the point has an impact on sort of each individual gradients. I guess there's a trade-off in the sense that you have to think about what the mini batch size is, but also how many steps you're taking. And it's hard to draw sort of a conclusive statement without sort of taking into account these two factors, I think. Does that make sense?
Absolutely.
It's the same as in, yeah, it's the same as in differential privacy in some sense that yeah, it's sort of the same type of effect. The more steps you have, the more potential for leakage you have as well.
Great. Thank you.
Absolutely.
I have one more question in the part one for the CISA framework. I'm wondering, in the scenario when multiple accounts decide to delete their accounts, and the worst case would be that they are evenly distributed in every slide. Every slide then they'll be retrained. And is there any way to mitigate this?
I'm not sure. Can you repeat the question?
So in the CISA framework, if there are multiple users that decide to delete their accounts, the worst case would be they are in different sharding. And yeah, in that case, every model needs to be retrained, leading to expensive computation. And is there any way to mitigate this issue?
Yeah, I mean, this is unavoidable in sort of the default setting where you uniformly partition the data. It's possible to anticipate this by trying to distribute the data in sort of a non-uniform way. So you could imagine that if you know that some points are more likely to unlearn, you could try and place these points in the same shard. And so that would hopefully minimize the number of shards you need to retrain as you get these different unlearning requests. The downside of that is sort of similar to the limitation I discussed with Tyler's question, in terms of sort of, you can imagine that if the points that are more likely to be unlearned, for instance, are from sort of the tails of the distribution, then placing them in a single shard might also impact the performance of the model on these points at test time. And so it might actually not be desirable to have this setup where you concentrate these points in a single shard. But that's essentially the best idea I can think of in terms of not having to retrain too many shards otherwise. But in some sense, all of the approaches have the same type of limitation, that as the number of unlearning requests increases, it's hard to avoid the cost of unlearning. So for instance, if you think about differential privacy, you have a similar problem where the guarantee is for a single point. The value of epsilon you prove is for a single point that you would want to unlearn. If you want to now unlearn a large number of points, then the privacy guarantee you have is not telling you anything about how close the models are with and without sort of this large number of points. And so there again, you're left without any sort of meaningful guarantee. So I think it's not necessarily a limitation of CISA per se, but it is a problem that is common to a lot of these unlearning techniques.
Yeah, thank you. It makes sense.
Yeah, no, it's a good question.
I guess I kind of opened up one question I have of in terms of industry, are you aware of how common this is of actually implementing unlearning frameworks, or is this still kind of cutting edge that not many have been integrating this?
Yeah, I mean, I've heard sort of anecdotal sort of evidence of people employing what I think is closer to sort of data retention policies that sort of have been in place for a while, where you decide sort of that your data has some expiration date, and so you could imagine you do the same with models, that you just retrain them from scratch after a while. I think most of the discussion that I've seen from industry has been sort of through research papers recently, as sort of people move to the task adaptation paradigm. And so there is sort of an uptick in interest, definitely in that part of the field. But it's hard for me to say, sort of speculate about what happens for other pipelines.
Yeah, I guess I'm just thinking that perhaps higher up management might just prefer spend the extra compute, retrain bi-weekly or something like this, and not have a risk of legal issues. I'm not sure.
Yeah, I think it's hard to know what is best without sort of knowing the kind of pipeline that is in place. Because so, for instance, in the example that I gave at the beginning of the talk, where we're sort of doing some form of task adaptation with prompting, we can certainly hope to do something sort of more efficient than naively sort of rerunning the data selection for the prompts regularly. And so I hope that people are sort of considering these kinds of approaches. But then you're right, like once you go to more generic pipelines, the training from scratch is sort of the best we can do as far as we know from the research. Yeah.
But to that, going back to the metric question, it seems like Nicolas, from your talk, my understanding is we still don't have great metrics for deciding whether a model is like unlearning a data or not. So then if we don't have a metric, how are we going to measure this? Like somebody requests, please go ahead and delete my data from your model. And we say, okay, we did it. Then how is a third party going to measure this?
Yeah, so right now there's no way to do this. And that's why in my group, we've focused mostly on exact unlearning. So that's why we've worked on seesaw and erase, because then we don't have to sort of define the success metric. Then moving forward, I hope that with sort of the work we're doing, trying to build from differential privacy and relaxing it. So again, these are the two approaches here that are in these two papers here. I hope that we can get to a point where people can actually expect to see sort of a bound on sort of the success of membership or the privacy leakage for their particular piece of data. But there is still, even in that paradigm, there is still trust that is needed, that what is being said is actually what is being done. And there, I mean, if we don't trust the entity training the model, we have to go, as far as I know, we have to go to cryptography, and there, like the scalability is an issue. Like we've done some work also on proving that models are trained in a fair way, or proving that models are trained with differential privacy. And of course, this work here on verifiable unlearning. And the common thread here is always scalability is an issue. Even if we can make very rigorous claims, it's just hard to envision this being deployed on the scale of sort of a language model or something along these lines.
I have one follow-up question on the matrix. So if there is one new matrix that are proposed, how to justify that this matrix is meaningful? How to justify this one?
I mean, that depends on, I think it depends on the motivation. Is it a privacy motivation? Is it poisoning motivation? So that's the first part. If it is a question of privacy, I think right now people are pretty set on this sort of type of goal to be able to show that you haven't trained on that particular point. But you're right. Like you could also have very different expectations from users to users, and that's something that I hope there will be more research to understand sort of what are different users' perspectives on what it means for their data to be unlearned. Because you could imagine there's some corner cases, right? There could be people asking to unlearn data that is already in the model because of other users, right? Multiple users could have the same piece of data. And so there, that's kind of a corner case as to like what you should do about that. And I think there's more research, and it's not necessarily a computer science only problem. It's sort of a socio-technical problem at that point.
Thank you.
Yeah.
I guess, well, thank you again. And yeah, it was really
My pleasure.
nice having you, and thanks for the presentation.
My pleasure. Thanks again for having me.
Fantastic talk. Thank you so much.
See you.
Take care.